So you know the meaning of multiplication of matrices as concatenating linear transformations. But in this video, I'm going to show you how to actually multiply the matrices. If I give you two matrices, multiply them. How do you do that? And the video is going to be divided into two parts. First, I give you the proof. So I'm going to put a mathematician's hat. And I'm going to say, okay, I'm a mathematician. Let me prove you how to do the multiplication. And then, in the second part, I'm going to give you the trick. And the trick is the way you will always do it. It's the fast way, okay? But since I'm a maths teacher, I really need to give you the mathematical justification. So let's start with it. So we were here saying that a matrix C being a multiplication of matrices B times A corresponds to a transformation in which we first do the transformation A and then we do the transformation B. Yes? So, proof of how to calculate the product of matrices. Let's give names to our vector V that we start with. Then we apply the transformation A. Then we apply the transformation B. And let's say that we end up with vector Z. Okay? And now this joint transformation, we call it transformation C. Okay? So what can we say about vector Z? Well, vector Z is equal to transformation B applied to transformation A applied to vector V. Right? That is obvious. So this is equal to transformation B applied to transformation A applied to vector V. But let's write vector V by expanding it in a basis. Okay, so vector V in general is V1 times E1 hat plus V2 times E2 hat plus dot 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 Vn times En hat. Okay, remember, in the most typical case, this is just Vx x hat plus Vy y hat. Yeah, but in general, it can be in an n-dimensional basis. Next, we apply one of the axioms of linear transformations. So we apply the linearity of the transformation A. Yeah. So what is the result? The result is that we have the transformation B applied to a vector which is a linear combination of the transformations A's applied to each of the basis vector, because that's what linearity means. So we have V1 times A applied to E1 plus V2 times A applied to E2 plus dot 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 Vn times A applied to En. Okay, I just applied the idea of linearity. But now I apply it again because B is a linear transformation. So we apply the linearity of B. And what do we get? So we end up with a linear combination using the coefficients V1, V2 up to Vn, but now applying B to each of the vectors, that we had initially. Yeah. So we would have V1 times B of A of E1 plus V2 times B of A of E2 plus dot 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 Vn times transformation B applied to transformation A applied to En. Okay? Now at the same time, from a different point of view, from the point of view that this is a transformation C, we know that Z equals transformation C applied to vector V. And by linearity, so if we do the same steps, by linearity we know that this will be equal to V1 times C applied to E1 plus V2 times C applied to E2 plus dot 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 Vn times C applied to En. Yeah? And we know that the matrix C, so matrix C is a matrix with the different columns being the transformation applied to the basis vectors. That's how we built a matrix. Yeah? So each of these terms here, this is the first column of the matrix C. This is the second column of the matrix C. And this is the last column of the matrix C. But from the previous point of view, when we wrote 7 in terms of A and B, we can identify that this column is actually equal to this thing, and this column is actually equal to this thing, and so on. So for example, let's make this even clearer. So the first column of matrix C, that would be C applied to E1, this is equal to B applied to A applied to E1. Right? That's what we just found. And what is A applied to E1? That is the first column of A. Right? And this is true for any column. So if instead of saying first, we say the ith column, yeah? So this means that wherever I have a 1, I put an I. And this is the ith column of A. So we see that the ith column of C is basically the ith column of A multiplied by matrix B. Okay? In other words, we get A, we see all its columns, and each column we multiply it by matrix B. So when we multiply each column by matrix B, we are getting this, which will correspond to the columns of matrix C. So I know this is a lot of words, but what it's saying, it's actually very, very simple. Okay, so let's do an example. If we have this matrix multiplication, so I'm asking you to multiply these two matrices. Okay, so let's say that this is matrix A and this is matrix B. So the result is matrix C, and matrix C will have 2 columns. So basically what I'm saying is that the first column of C is simply the first column of A, which is 0A, multiplied by matrix B, 1A, 0, 2, which is equal to 1 times 0 plus A times A, 0 times 0 plus 2 times A. That will be the first column of C. Okay, so first column of C is A squared, 2A. And the second column of matrix C is matrix B multiplied times the second column of matrix A. So pi 1, which is equal to 1 times pi plus A times 1 and 0 times pi plus 2 times 1. So this will be the second column of C. So we can write it as pi plus A and 2. And that will be the result of this matrix multiplication. So this will be equal to B times A. So now we know how to multiply it formally. Now, this was like the rigorous proof of why it works. But let me give you the method or the trick that you will always use. So if you want to multiply these two matrices, 1A, 0, 2, times this other matrix, 0, pi, A1, we are going to do a very similar trick to the trick I showed you for multiplying a matrix times a vector. So the way we do it is we get the second matrix, and instead of writing it here on one side, we move it upwards. So we place it here. And now this leaves this gap here. But this gap now has 4 slots. And this is where our resulting matrix will go. Yeah. So how do we fill the first slot? So the first slot will be the dot product between this row and this column. So it will be 1 times 0 plus a times a. It will be a squared. Yeah. Now, the next slot, the slot that goes here, will be the corresponding row that points to it, dot product with the column that points to the slot. So it will be 1 times pi plus a times 1. It will be pi plus a. That will be this slot. Next slot will be the corresponding row that points to it, dot product with the corresponding column that points to it. So it will be 0 times 0 plus 2 times a. It will be 2a. Yeah. And finally, the last slot, I'm not going to draw it, will be 0 times pi. By the way, I erased that 2, sorry. It will be 0 times pi plus 2 times 1. It will be 2. And that's how you multiply two matrices very easily. Notice that the result is the same that we got earlier. Yeah? So this is the way that in practice you have to multiply the matrices. Okay? So now you know how to concatenate linear transformations and calculate the matrix that corresponds to the concatenation. See you in the next video.